Hi, everybody. Welcome back to the fourth part of the lecture on the solar system. This is the fourth and the final part for this chapter. Hopefully, you've looked at the other three, and if you haven't, you better do it relatively quickly because on Thursday, the 23rd of April, we're going to have an exam on this chapter. So hopefully you get a chance to review everything because I'll be taking the exam directly from the slides that the lecture slides. So last thing we talked about was the fact that the comets, the debris that comets leave in their path, uh, is the has causes meteor showers, and we talked about the meteor showers being annual events where we know where the Earth is and we know the orbit of the Earth, so we know when it's going to pass through the debris left behind by a comet. And we also talked about the radiant of a meteor shower, and the radiant of the meteor shower is the area in space or the constellation in the sky from where the meteors seem to be coming from. That's what the radiant is. And let me just give you a little examples here on some of the missions we had to actually observe comets close up. And the first one, I told you, one of the most famous comets that people know about is the Halley's Comet. And Halley's Comet, I told you, came very close to the Earth in 1910, and its period is 76 years. So it visited Earth again in 1986. Okay, and in 1985, the European Space Agency, ESA, they call it, sent a spacecraft named Giotto. Giotto was the name of an Italian astronomer. And they named the spacecraft after them. And its mission was to try to go and photograph a comet close up. And as you can see here on the left-hand side, here is an image, one of the images taken by the Giotto spacecraft of Comet Halley back in 1986 from a distance of only 2,000 kilometers. It actually got very close. You can see here the bright areas here as the sunlight is, hence the sun is actually on to the left-hand side here. It's illuminating this side of the comet. Although this does look like a tail, this would be part of the tail, it's not. Okay. This is the surface that's exposed to the sun, so the material is being melted and comes off the comet in this direction. And so this is an image taken by the Giotto spacecraft, and the spacecraft, I think, was hit by a few particles from the comet because it went so close. It kind of disabled it, disabled certain cameras. It had the antenna that was pointed towards the Earth displaced and moved away, and it no longer was when pointing to the Earth. They no longer received images for it for about 2 weeks, and then they recovered it a couple of weeks later after it passed Halley's Comet. But this was a mission when Halley's Comet had gotten pretty close to try to get a first picture of the comet. And what do we see here? If we look at the structure of a comet, I told you comet is a dirty snowball, right? It's a frozen gases and everything. And typically, a comet has a crust of material that either freezes and refreezes. Okay, as it melts, the outer surface becomes almost like a gas. It really doesn't become a liquid because in space, usually don't get things go. They go directly from gas, from frozen to gas. There's no liquid stage. And so it forms a little crust around it, and then sometimes due to the expansion and contraction of temperatures, you can actually get these little cracks inside the near the surface of the comet. And these comets can liberate gas, and you'll see these jets coming out. And as the comet warms up and comes closer to the sun, it releases this material in form of a jet, and the jet can actually make the comet spin around. And as I'll show you later on, I'll show you some more images from other comets. You can actually see the comet spinning as a result of these jets just erupting on the surface. If you remember the movie Armageddon, I believe there was Bruce Willis and his company landed on a comet, and showed how this material just blasts right off the surface as it starts heating up. So this was one of the first images we had of a comet way back in 1986. This is the only image we ever had. Back in then later on in 2004, the European Space Agency performed another mission to go to a comet. This one was going to be to link up with a comet that had a name 67P. It had a strange name. That's its catalog name. But the mission was called the Rosetta mission. Rosetta was going to rendezvous with a comet. And the main spacecraft was called the Rosetta. That was the mothership. And the mothership was designed to deploy a smaller object about the size of a dishwasher, as you can see right here, called the Philae lander. And the lander was designed to land on the comet after the mothership was to orbit and find a suitable place for it to land. The mission launched in 2004 and took 10 years to get to the comet. First, it had to build up speed in order to reach the comet, because essentially it's like hitting a bullet with another bullet. And so what it had to do is orbit the inner solar system quite a few times to go very close to planets to get a gravitational assist to speed it up in order to rendezvous with the comet. So you can see it's going around here if you look at the details in this diagram right here. The details of how it took about 6 orbits around the inner solar system before it was ejected out and rendezvoused right here with the comet. And so this was a very ambitious mission. And so let's look at, I have a video here. Let me just show you the video, a little about this Rosetta mission.
"10 years ago, and Rosetta's journey began. The spacecraft set off for a distant rendezvous with comet 67P Churyumov-Gerasimenko. It used a gravitational kick from Mars and 3 from the Earth, circling the Sun almost 4 times and travelling over 6 billion kilometres to reach its destination. Along the way, Rosetta studied asteroid Steins and Lutetia. But the main priority has always been to examine a comet close up, see how it changes as it nears the Sun, and attempt the first ever landing. There wasn't enough sunlight to power all but the essentials in deep space, so Rosetta was placed in temporary hibernation in 2011. It spanned just once a minute while facing the Sun, so that the solar panels received as much sunlight as possible. Meanwhile, the internal alarm clock was set for January the 20th, 2014. When the day came, ESA's European Space Operations Centre, ESOC, in Germany, listened out for a weak signal from the spacecraft. And after a nail-biting wait, the signal arrived. Within 6 weeks of the wake-up call, all of Rosetta's 21 onboard instruments had been activated. In May, Rosetta put on the brakes and slowed down for the rendezvous. By the beginning of August, 9 thruster burns, including a small test burn in early May, ensured that the relative speed between the comet and the spacecraft had been reduced from 750 metres per second to 1 metre per second. As Rosetta got closer, its destination became clearer, and it was a surprise for everyone to discover that the comet was shaped like a duck. Rosetta arrived at its destination on August the 6th. Shortly afterwards, it became the first spacecraft to orbit a comet. The world's media gathered at ESA's Paris HQ in September to discover where Rosetta was planning to land. There were 4 possible sites, and one on the head of the duck-shaped comet, Site J, got the job. While the orbiter instruments are studying 67P, its cameras have produced some incredible images, some from just 10 kilometres away. But now it's time to get even closer and prepare for the first ever landing on a comet.
So as you can see here, this is the first images, really high resolution close-up images that we've received from this Rosetta mission and the Philae lander as it was being deployed to land on the comet. And you can see this is a frozen body. Okay, you can see some of the jets coming off. If you look in this right-hand picture right here, you can see some of these jets as the comet is warming up, coming closer to the sun. So that's some of the high speed images, the high resolution images. Let's show you another. Here's an animation of the rotation of the comet caused by the expulsion of gas from the jets. If you can take a look here. Let's look at it here. Here's actual pictures taken from the satellite. You can see these little jets. Oh, you see a big one there. There was a big one coming out, and that causes the comet to rotate. Okay. Here's another. Let's talk about the landing of the Philae lander, how the lander was designed to go onto the comet. Here's a short video of that.
Once the flight dynamics team has given the go-ahead, the Rosetta spacecraft will maneuver itself so that its Philae lander is on the right trajectory for the landing site. Rosetta will release Philae when approximately 22 kilometres from the centre of the comet. A signal confirming the separation will arrive at ground stations on Earth 28 minutes and 20 seconds later. The landed descent will take 7 hours. On the way down, Philae will take a series of images, including a farewell shot of the orbiter. Some of its onboard instruments will sample the dust, gas and plasma close to the comet's surface and measure any magnetic field. The Sesame experiment, which contains 3 instruments, includes one called CASE, located in the lander's feet.
CASE detects the touchdown, the moment when the lander hits the surface, and also it has active emitters that emit acoustic waves in one foot, and they go through the surface and can be detected in another foot, and we can derive the mechanical properties of the soil of the cometary nucleus this way.
The 3 lander legs will absorb the momentum and use it to drive an ice screw in each foot into the surface. At the same time, 2 harpoons will fire to lock the probe onto the surface, and a small thruster on top will counteract the impulse. Once anchored to the nucleus, Philae will begin its primary science mission, based on its initial battery lifetime of 64 hours. The lander also has solar panels, and hopefully they can recharge the batteries and extend Philae's lifetime. Above the lander, after separation, Rosetta will move away from the comet and reorientate itself to communicate with the lander. If all goes well, communications will be underway around 2 hours after separation. The first images from the descent are also expected within several hours of this point. The timing and precision of the landing maneuvers are crucial. But once safely on the comet, Philae will undertake its in situ experiments. Its first operation will be to take a panorama of its surroundings, and within hours we will see the first ever view of a comet from its surface.
Okay, here's the some of the first images returned by the Philae lander. One of the problems, there was a problem with this mission, was that when the lander was going to the surface, the little harpoons that they had to anchor it to the surface did not fire. Because it has such a low gravity, it's very hard to hold the lander to the surface. So they had these harpoons supposedly designed to anchor it there, and they never fired. As a result, what happened was that the spacecraft bounced up for about 2 hours and then crashed back on the surface and then bounced up again and crashed a third time, and then it was lost. And for 2 years, scientists were looking for it, and finally they found it. Here's some of the images. They found the lander. It really didn't complete its mission. Here you can see right here is where this lander was, and here is the lander. Finally, you can see it laying on its side, and one of the problems was the solar panels were not pointed towards the sun, so the batteries ran out relatively quickly. But these were some of the close-up images returned by the lander. But as I told you, it took 2 years to actually find where it was after it stopped functioning when it started to land on the surface. Here's some of the close-up images taken of the comet. These are the frozen bodies. Here's one, the one on the left here, around 5 kilometers above the surface, and here is about 20 meters above the surface, what the thing looked like. So these were some of the images returned by the Philae lander as part of the Rosetta mission. All right, what I want to talk to you about now is something a little different. Okay, we talked about comets, we talked about all the different objects in the solar system. Now, what I'd like to talk to you about is how did the solar system form? Okay, we've kind of maybe talked about it in little bits and pieces throughout the semester. But the general theory of the formation of any kind of a star and of a solar system is this idea of nebular contraction. And remember, a nebula is a collection of gas and dust in space, mostly that's been ejected from stars that have died before it have exploded and send the material out into space. And as this material starts collecting, gravity actually makes it contract, actually gets it to start collecting together. The mutual gravity of these pieces starts pulling it together, and slowly this cloud of gas begins to contract. And what happens is, as it contracts, it forms a disk that you can see down here. Here's a disk of this material. Here's this cloud of material starting to contract. Okay, those little arrows represent contraction. And as the thing starts to contract, it begins to rotate. Okay, and as it begins to rotate, it contracts even more. And as it contracts even more, it starts spinning faster and faster. And it's interesting is why does a spinning disk tend to increase its speed? Why does it go faster and faster as it gets smaller? And that's a process in physics we call conservation of angular momentum. It gains speed by this principle of conservation of angular momentum. Let me talk to you about that for just a moment, what that means. Conservation of angular momentum is similar to what you've seen before. Here I show you a diagram of an ice skater. And sometimes you'll see an ice skater, and when she has her arms separated from her body, she starts to spin, and then as her arms move closer together, okay, as she bundles those arms in, the rate of rotation, the rate of spinning gets faster and faster. You've probably seen it a lot. Very slow when her arms are spread out, and as she brings her arms in, she starts spinning faster and faster. That's called conservation of angular momentum. It says that when you have a large radius, when the object is fairly large, it will spin slow. And what happens is, as it becomes smaller, okay, as it becomes smaller, it would have to spin faster to maintain its angular momentum. That's what we mean by conservation of angular momentum. Something large has a slow rotation, and then when it gets small, the rotation gets faster, just as a ice skater gets faster when she draws her arms in and she becomes smaller. So that's what happens now in this cloud of gas and dust as it becomes gets closer together by gravity. It starts spinning faster and faster. It forms a disk, okay, and its rate of rotation increases, okay. And then there's what takes over is in this nebular contraction is this theory of condensation. Well, what happens is as this cloud of gas, and you can see it evolves, you can see as it evolves, it's going from the top of the diagram down to the bottom. These grains of dust and gas start collecting, and in the center, they start colliding. These pieces collide with one another and actually builds up some heat. Okay, and as it contracts and it spins faster and faster, it becomes more and more dense in the center, and the center of the object becomes quite a bit hotter. You can see here it's starting to glow red from the heat, and there's the density of particles is more here than it is out here. It's cooler out in the outer part of it because it's less dense, less collisions, and it's hotter in the center. And over time, over millions of years and possibly even billions of years, okay, what happens is it gets hotter and hotter and hotter, and in the center here is the proto-star or the proto-sun. As these objects and the gas collides, the heat builds up, and then surrounding the proto-sun or the proto-star are also different pieces of material that start forming planetesimals or protoplanets. They start forming from the material that's surrounding this protostar. And then after several million years, what can happen is as this region becomes hotter and hotter and hotter, and it contracts, it can get hot enough to start the process of nuclear fusion. And nuclear fusion, remember, is the process that fuels the sun. And this is the process that creates light and energy that gives us our sunlight. So now the star is born, okay, just like the movie, the star is born after the heat gets high enough for nuclear fusion. And you'll see many planetoids or planetesimals are surrounding this. And over hundreds of millions of years, as some of these planetesimals, they collide with one another and become larger and larger planets. So you may have hundreds or thousands of these small planetesimals surrounding this proto-sun, which was formed from the collapse of this gas. And then you have finally what we have now, for example, in our solar system, is we have 8 planets. There may have been thousands before that, but then they collide with one another, they collect planets, grow in size, and this is how a solar system forms. Okay, you can see the material that is ejected in space from when stars die essentially gets recycled, and over millions of years, then the disks start to spin, temperatures rise because of collisions, and proximity of then the density of material in the center, and if the temperature gets hot enough, a star lights up and the material that's left over surrounding it becomes planets. And that's why I told you early in the semester, when you see a star, every star probably has planets going around it. Okay, we have found quite a few of those. We're going to talk about those in just a minute. But you can see this is the origin of the solar system. This is how solar systems are created. Okay, and how do we know this? Okay, how do we know that that's true? Well, we can look up into space and we can see examples of solar systems starting to form now at this time. Here's a star right here. Okay, this is a diagram, by the way. This is not a photograph. This is just a diagram. But here's some data from a star called Beta Pictoris. There's a constellation called Pictor in the southern hemisphere, and Beta is the second brightest star in the constellation Pictor. But if you look at it closely, what you see is this is a thermograph. It's actually a plot of temperature surrounding that star. And as you can see, it looks like a pretty large star. It's a star just or a solar system just starting to form. You can see it's hotter here in the center where it's red and cooler at the outside. This little central area right here is about the size of our Kuiper belt of our solar system. And if we expand this region, we expand it into this diagram right here, we can see that the central area is becoming hot, the outer areas are cool, and what we suspect is going on here is that a star is beginning to form. And there's clumps that we can't see yet, but this diagram shows the clumps where planets are going to start forming. If we look at one a little more evolved, here's another system. I forgot exactly which one this is, but here's an image of a proto-solar system starting to form. Here is the central area where the star is, and you can see in this diagram right here, when they put a little disk here to hide the brightness of the star so you can see the outer extremities, you can see here little planets starting to form. You can see clumps of material aggregating to try to form planets. So we can see this happening. If we look out in space, we can see all sorts of stars in different stages of formation. Stars that have died and stars here that are just forming. And this is how we develop our ideas of how our solar system started. Here's another more recent research showing these proto-disks of these solar systems forming. You can see here these disks of material surrounding stars. Okay, here's this one star around this star called IM Lupi. Okay, I guess it's Lupi. Lupus is a constellation in the southern hemisphere again. And here is another showing a central star and the material surrounding it that's going to become planets. So you can see here that planets are a necessary byproduct of star formation, and stars form from the nebular contraction of gas and dust, and then this condensation of material to become planets. So that's how our solar system, we believe, is formed, and that's how we believe other solar systems are formed. Okay, and some of the things we have to look at as a solar system is forming. Okay, one of the questions that we can ask is what determines where planets form? Okay, we notice that in our solar system, the rocky planets, okay, the terrestrial planets as we referred to them earlier, they formed closer to the sun, and the gas planets formed further away from the sun. Well, why are the rocky planets close and the gas planets further away? Well, we know the gas planets are colder, and we know that outside in the solar system, the temperatures were lower in the outer parts of the solar system because they're further from the heat source in the center. And we know that the rocky planets looks like they all formed very close to the sun because that's where the rocks could withstand the high temperatures, and as soon as as you consider the temperature, if you look at this curve right here, okay, look at the temperature as you move away from the sun. This is a plot of temperature, okay, as you get further and further away from the sun. And this is the distance from the sun in astronomical units. Remember, an astronomical unit is the average distance of the Earth to the sun. So you can see here the temperatures close to the sun were fairly high, and that's where the Earth formed. That's where Venus and Mars formed, because there, as soon as the temperature dropped to where lava, if you will, think of molten rock, as soon as the temperature got to a point in, let's say, 1,000 degrees where molten rock can condense, those planets formed. But as you go further out, the temperatures get lower, and the material there, gases, into the high heat, they'll stay in a gaseous form. But as they get cooler and cooler, those gases can contract, and they actually form the outer planets. Jupiter, Saturn, Uranus, Neptune formed in the outer regions where the temperatures were lower. So, what is it that determines where planets form? It's temperature. Temperature in this cloud of gas will determine where the planets form. That's why the rocky planets or condense out at a much higher temperature. Okay, condense out meaning they will become solid, if you will, at a much higher temperature than gas planets. And the gases will only freeze out and become planets further out where the temperature is lower. So temperature is the deciding factor in where planets form. Let me talk to you now about planets beyond our solar system. Sometimes you'll see in the news and you'll hear that we discover planets going around other stars, okay? And we call these exoplanets or planets going around other stars besides our sun. And there have been quite a few of these exoplanets discovered. It's difficult to see exoplanets directly because these stars are so far away. The planets, remember, don't shine by their own light, and they're extremely dim. So there's really no way we can directly observe the exoplanet or another planet going around a star. So how have we been discovering these if we can't see them? The light of the star is just so bright, it completely washes out any detail because the planets are relatively close to the star when they're very far away. We can't see the distance between them and their stars, and they just get washed away in the light. So there's no way to optically see it with a telescope. All right. What we have to do is detect it indirectly by the influence of a planet on its star. And that's why I want to talk to you now about some techniques that we use to actually find planets beyond our solar system, what we call exoplanets. Now, some planets can be discovered, I told you, by their influence on the stars. Okay? And they're discovered by looking at the wobble that they create in their parent star's orbit. Okay? If a star is extremely massive and a planet is fairly massive, we know that the star will pull on the planet and the planet can actually pull on the star. And as you can see here is a chart of showing you when we look at a star where we can measure its velocity, that is its speed either moving towards us or moving away from us. We can measure that speed, and we're going to learn how we measure that speed in the next chapter when we talk about analyzing the light from a star. But suffice it to say for now, we can measure the speed of a star, of not how far across our line of sight it's moving. We can't measure that velocity, but we can measure the velocity if it's coming closer to us or if it's moving further away from us. And if you can see here, one of the stars, a star here, the velocity of the star was measured. And here it is over a series of about 4 or 5 days. We're plotting the velocity of a star. And we can see here that the velocity, the speed is increasing, and all of a sudden then it turns around and starts decreasing, and then goes back up, increasing and decreasing. And this is some periodic function. We can see the increase and decrease. And what is it that's causing this star to speed up and slow down? And what it is the influence of a planet. A large planet is around that, and you can see here, you can even tell how long does it take the planet to go around the star. Well, look at a whole period here of this wave, if you will. A whole period takes roughly 3 days. So it looks like this planet is going around its star in almost 3 days. So we can see this wobble, we talk about the wobble in the star's orbit caused by the gravitational influence of a large planet. Here's another one. Here's actually one that's actually very quick, right? Here's one that goes around its star in 3 days. All right, 3 days is fast. We know that the closest planet to the sun, to our solar system, is Mercury. That takes 88 days to go around. So this technique is really sensitive only to fairly large planets because then they have a larger influence and usually they will travel faster around their star. Here's another one. Here's another star in the constellation of Andromeda. I believe it's called Upsilon Andromeda. Here you can see many little bumps up and down of the star speeding up, slowing down, speeding up, slowing down. This could be many planets that are actually going around the star. We can actually sense quite a few of them, the influence of a lot of larger planets. And you can see this plot is now over several years. We're not talking about days, we're talking about years. So here's a detection, okay, of an exoplanet by its influence, by the wobble it causes in its star's orbit. So that is one technique for us to find exoplanets, is by detecting wobble in the star's orbit. And you can see here this is the orbit. This is just to show you how close these planets are to their stars. All these planets that we've discovered are probably inside the orbit of certainly between Mars and Earth. Okay, if we just compare distances compared to distances in our solar system, they're relatively close to their stars, closer than Mars and Earth. So typically the sensitivity we have to these large planets is when they're very close to their star and they're extremely massive, so that we can see this gravitational influence. So that's the first way we can detect exoplanets. There's also another, and this is a more popular way, a little easier for us to see. And let's talk about this. Sometimes we can get lucky, and when we're looking at a star, the plane of that exoplanet going around another star, the plane of its orbit can actually pass possibly right in front of the star. If the solar system is lined up so that the planet, from our viewpoint, the planet passes in front of the star, what can happen is, if we look at it for a small amount of time, we can see here is a star, and then after a short amount of time, look at the planet now starting to pass in front of the star. And as time goes on, the planet moves a little further, till finally it moves away. And what happens then if we look at the light from that star? Well, here's what we have plotted down here. We have the intensity. The light from the star looks like it's at a bright point right here. As soon as the planet now starts to cover some of that star, the intensity of the light drops. And as long as the planet maintains its position in front of the star, it's going to lower the brightness of the star. Okay, this is essentially like an eclipse, if you will, of a star. Okay, we're looking at an eclipse. We're looking at the planet passing in front of it. And as soon as the planet then moves off, you'll see the light intensity raise again. So this is amazing. Look at this. We can actually look at this dimming of the star's brightness, or of the star's luminosity, we call it. And we can actually detect planets by looking at the dimming of the parent star's brightness. Okay, and you can see that larger planets, okay, if the larger planets have greater area here, they will block more and more of the intensity of the star. It's going to be difficult, as I told you, to detect small planets because they will not cause as much decrease, if you will. Look at this decrease in the star's brightness. So these techniques, as I told you before, the wobble in the star's orbit and this dimming of the star's brightness, they usually are detected by large planets. Large planets are the ones that form this. And in fact, I want you to remember that this technique of periodic dimming, so let's say this can happen, this not only happens one time, but it happens several times in order for us to confirm that a planet is actually orbiting a star. Okay, it has to be periodic, that every so often you'll see that all of a sudden it dims. That's because the planet is orbiting the star. So this technique, though, is only sensitive to planets that are lined up specifically that'll pass in front of their star. If the planet is moving around the star like this, it will never cross in front. It will never see it dim. So this technique, although it's good and it's detected thousands of planets from the Earth and from space telescopes, we can only determine if a planet is there by this technique of periodic dimming, only if the way the planes are lined up. It has to be exactly in the right plane. If it's not in the right plane, as I told you, if it travels around here, the planet in this direction, the orientation is such that we'll never see it. So it has to be lined up just right. So we're only sensitive to a few things. So here's what I want you to remember. A couple of ways we can detect exoplanets, okay, is one, by looking at wobble in the star's orbit. We can see the star gets perturbed, gets changed by the gravitational influence of another star. And second, we can get periodic dimming of the star's brightness if the conditions are just right and it's lined up right and the planet is large enough, it can actually dim the intensity of the star, and we can actually detect a star that way. And we've discovered many planets like this. Most of them, I told you, again, if you look at this diagram here, the orange are the distances of planets to their stars. They've pretty much been found only very, very close, because they have to orbit in a reasonable amount of time. If we see periodic dimming, okay, over the course of days or weeks or something, that's how long it takes the planet to go around. However, in our case, for example, if you look at some of the outer planets like Jupiter and everything, Jupiter takes about 15 years to go around the sun. We would have to look at periodic dimming over 15 years. Okay, we've only been observing these things for maybe 10 years or so. So we're only going to see periodic dimming compared to the times that we look at it for. Okay, so we only see things that happen relatively quickly. Okay, and most of them, I told you, have larger masses. So they're mostly masses as large as one of our largest planets in the solar system, Jupiter. So we're finding only large planets because those are the ones that either perturb the orbits, the wobble, they cause the wobble, or they can cause the dimming. We only see the larger ones. It's much, much harder to see the smaller ones. But as telescopes are developed, we'll start seeing more and more smaller telescopes, and more and more planets, as we start increasing our sensitivity in terms of our observational capability. Okay, so that's it for the chapter. Okay, we've completed the chapter on the solar system. All right, let's just review some of the important things that we talked about. And one is, what is a solar system? It's a solar system. It consists of a star like our sun and everything else orbiting it. Okay, the comets, the asteroids. Okay, and what are asteroids? They're the material that are left over from when our solar system was formed, and they can be either rocks or metals or combinations of both rocks and metals. And most of the asteroids live in a belt of material called the asteroid belt between the orbits of Mars and Jupiter. Sometimes we said, as you saw in the video that you watched for your writing assignment, that sometimes these asteroids collide with one another and can then be gravitationally attracted to the sun. They can cross the orbit of the Earth and possibly collide with Earth. And we've had several examples where asteroids have collided with the Earth. Asteroids have collided with the Earth 65 million years ago, one that was only 6 miles in diameter, and killed 70 to 75% of the life on Earth, including the dinosaurs. They all died within a period of perhaps several days. Okay, comets are also go around our sun. Okay, they orbit in the Kuiper belt. We said way beyond the orbit of Neptune, and they are icy objects. They are also believed to be formed early in the solar system, and these are not made mostly of rock and metals like asteroids are, but these are made of gas. The gases are frozen gases. They're carbon dioxide, nitrogen, some water ice too, and these mixed in with maybe just a little dirt. Okay, that's what comets are. Okay, We also learned that most of the major planets, they orbit the sun in the same way. We can see all the planets go around in a counterclockwise direction when we view them from the North Pole, if you will, from looking down. And why do they do that? Well, remember, the solar system formed from this disk of material that was rotating, and everything continues to rotate in the same direction as this primordial, if you will, or this beginning nebular contraction started. Okay, they also lie in the same planets, lie in the same plane. That's the plane of the ecliptic. We talk about it because that was the plane formed by the disk of material as our solar system was forming. We also talked about the 4 terrestrial planets, okay? They're rocky, they're small, they're dense. I encourage you to remember some of the differences, in fact, between the terrestrial planets and the outer or Jovian planets, which are gases. It's probably a good idea, as I told you, to remember some differences, okay? We also learned about the nebular theory of the solar system formation, where clouds of gas and dust caused by material that was ejected from stars that have lived in the past is out in space, and it gradually collapses under gravity. It spins faster and faster due to a property we call conservation of angular momentum. That conservation of angular momentum requires that as a spinning disk gets smaller in size, it spins faster. And then what happens towards the outskirts where the temperature is lower, condensation theory says the dust grains will start collecting, forming planets. And where the temperature is higher, okay, the rocky planets will condense out at higher temperatures, okay, than the gas planets. So gas planets are formed where the temperature is lower, further out from their stars. Closer to the stars, the only ones that can take the temperature are the rocky planets. Okay. And finally, we found that exoplanets have been discovered in other solar systems. That is, planets going around other stars. Okay, and as I told you, we can't see them directly, but we see them indirectly. And most of these objects are very large, and they orbit closer to the sun because that's our techniques are more sensitive to those. And remember, the 2 ways we can detect exoplanets is by looking at and detecting the wobble in the star's orbit caused by the gravitational influence of a large planet that's pulling on the star. So sometimes it actually pulls it towards us or possibly pulls it away from us. That's what we mean by wobble in the star's orbit. And also, if the conditions are just right, as I told you, if that exosolar system is lined up just right, and this technique is only sensitive if it's lined up just right, sometimes we can see the planet passing in front of the star. And we can see this periodically as the star orbits as the planet orbits the star. We can see the luminosity of the planet dimming. So the second technique of periodic dimming of the star's luminosity is another way of detecting these exoplanets. All right, and that's pretty much a summary of everything. I encourage everybody to review for the exam that we're having at our next class, and you have all 4 videos there. It would probably be a good idea to quickly review some of those videos because the test will be, again, just like we had it before. It'll be online. It'll be in 4 different sections: the true and false section, the multiple choice section, the fill in the blank, and the essays. The test will be given during normal class hours. You can't choose what time you want to take it. It will only be given during our normal class hours. So please pay attention to that, to the times of our class, and that's when the test will be open for you to take on Blackboard. So I encourage you to review what we've done today, review the other notes to prepare for the exam. Hopefully you'll do well and for the test coming at the next class. Thank you.